Alrighty, so before I get onto the stuff, quick announcement, very quick. For your lab number 1, I'm going to give you the solution for sure today. I'm gonna work on that as my first priority. Once we finish our class today, you should really receive it hopefully by the beginning of the office hour today. You can take a look and then try to compare yours with mine. On Wednesday, I'm going to go over maybe the solution together with you. It's going to be very fundamental for your upcoming assessment, for the final exam as well. So today, for sure, solution. That's for lab 1. And for your lab number 2, it's going to be next Monday. And that one there surely is going to require set relations functions for you to actually master what's going on in the lab. The lab there actually can generate many possible questions in the assessment. So I would suggest spend enough time on that, working on that. And as usual, I'm going to give you a solution and also walk you through the solution for sure. But for those of you who might be very keen to get started right away, so bear with me, right? You really need to make sure you get through all the materials for the review. And then we'll try our best to finish the most part today. If not, then we'll definitely use a little bit of time on Wednesday as well. And for your written test number 1, just to look ahead, okay? Let's now review the course calendar together just to get some expectation. Okay, sorry, not here, 3342. If you look at the semester calendar over here, we are now here today. Your written test number 1 is upcoming right before the reading week on February the 16th. The date is fixed, okay? You can expect me to give you some guidance, like a PDF guide around the beginning of the previous week. I'm gonna give you some guidance about what you can expect on the test, coverage for the test. Most likely it's gonna cover up until maybe lecture number 10, most likely, but I will confirm. And then I'll also give you guys some practice questions for you to try. If we got enough time in the class, we can also go over them. We can even schedule some review session for you, optional, right? We'll talk about it. You can just pay attention to my announcement. All right, that's about what's happening right now for the course, and very soon, before the reading week. We are moving just past 1/4 of the course already. And we're getting to the interesting case studies very soon, but we just need to make sure the foundation is solid. So for today, let's continue. And the 2 exercises I assigned you guys to do is about how you can rewrite 2 relational operators. I'll switch to iPad in a moment. One is about how you can rewrite the image. Oh, actually, I can switch right away. And then we can talk about the answer. Okay. So one question there was to rewrite the image. The other one is to rewrite the overriding operator. All right. Of course, you can find the answer already in the lecture slide. But let me just give you a little bit more intuition about the answer very quickly. And then from there, you should definitely expect maybe more algebraic properties I might give to you maybe later. Okay? Let me just go to my cheat sheets over here, just in case I say anything wrong. Okay? All right, for the first one, what we want to do is we want to rewrite the relational image. So R is a relation, and then square brackets is a syntax. And we're going to put some little s over here. This is a set. Okay, so S should be in the domain of R. Should be. If it is not, the image will just be empty, because nothing we can map to, right? Should be. Otherwise, result is empty, because nothing can map from outside the domain to anything. All right, how do we rewrite this? Okay, if you think about what we are doing here for the relational image, basically what we are doing is you're trying to somehow find out, let's say little s contains, let's say A and B. We want to find out all the pairs that has to do with A and B. So these are all the pairs that has to do with the domain value A and B, and nothing else. Okay, so this should really give you some very quick idea about the restriction idea, right? We want to restrict our original relation just to those pairs whose domain value over here can be a member of the little set. That's the input, right? That's the first intuition. Let me write something down just to begin with. If I write something like this, restriction, are we restricting the domain or the range based on what I just mentioned? Should be the domain, right? Because we're talking about, we want to keep only those that has to do with A and B, for example, right? I'm talking about domain value. That's number one, okay? Let me just clean it up. Okay, so it should be domain restriction, and you guys should really get yourself familiar with the syntax. So this will be a domain restriction. I would say if you can already think until this step, it's a very, very promising, almost to the end. But can we say they are equal? Can we or can we not? That could well be another written question for you, right? Which will require your justification. Can anyone justify whether this might be okay or it's not okay? If it's not okay, I want to know exactly why. And then, okay?
It's a pair, right? So we have to think about the range of the
Okay, it's a pair. Okay, getting very close. Thank you. So basically, the more precise answer goes like this. The left-hand side is just a set of single elements. To be more precise, a set of range values. This guy over here, by doing domain restriction, is going to return back to you another relation, which is a set of pairs, rather than a set of range or domain values. So that's why they are not exactly comparable. You can think about this one here is a set of range values. Whereas, if you look at just this one over here, is just another relation. And if you understand what's really the error, so now how can we fix it, right? That's really the beauty about applying relational operation. It's almost like doing algebraic, doing algebra. So if you don't find A plus B works, you can say A plus B may be multiplied by C. If it doesn't work, let's do another operation, right? Every time if you apply some operation, it's always going to return to you something, like accessor. So you can always combine different results together. So now, how do we fix it? We know that we should really get some range value, right? So that's why you should really put the range of that, not domain. I can easily change this, rather than range, change that to domain, and ask you whether they are okay or not. And you definitely need to justify, all right? Any question about the first exercise? Okay. Do you need to memorize the property? Not necessarily, but if you really understand it very well, you can easily come up with it, maybe during the test. That's the first one, okay? The second exercise was about the relational overriding. And that one there, I would say if you ever have to memorize any detail about the overriding, I would say memorize that. There are two cases. Case number one, you're going to take the entire input relation. Number two, you're going to take those pairs in the original relation R that has its domain value not in the input relations domain. It sounds a bit weird, right? Let's take a look, okay? What's going to happen is if you say, I want to do relational overriding, overridden with, let me draw a little bit better. And in the written test, let's say if there's a handwritten written test, be nice to me and the TA. You want to draw the symbol accurately, okay? It's a triangle. Be careful. But you got time to practice until the final exam. All right, overriding. Don't forget you got something like this, right? And of course, it looks very similar to the something like this. If you put something like this, what would that be? That one is nothing. It's not even a range restriction or subtraction, because if you do range restriction or subtraction, you should really point this way. So this one here is simply nonsense, right? Be careful, right? Okay, so let's say I want to be overridden by another input. Always remember this guy here is a relation. Okay? The result of the relational overriding is going to be just another relation. Okay, let me just put here. This will be just another relation. And how do we compose that particular relation? Two cases. Case number one, very straightforward, no-brainer. You just put directly this t, the input over here. All right? And union with another one. Another one goes like this. Basically, I want to keep the original relation over here. However, for any pair whose domain value happens to be in the domain of t, I want to get rid of them. Well, the getting rid of part sounds like a restriction or subtraction. Subtraction, right? I want to get rid of something rather than restricting to just that particular set, right? It's a subtraction idea. So what I should do is I'm actually going to say, I'll give you the answer directly. Let's talk about it. It's going to be another relation over here. I want to get the original R over here, but I want to filter out anything that has to do with the domain value that's in the domain of t. Are we okay so far? Okay. There might be another way to try. I'm thinking aloud. This part over here. Is it possible, rather than using domain subtraction, can we use domain restriction instead? Here, it says that we want to subtract out the domain of t. It would be as if we want to restrict it to something that's in R, but not in t's domain. Agree? Okay? So why don't we try that intuition? What I want to do is, I want to do R, but now I want to do domain restriction over here. And this part over here, okay, I'm going to write it down elsewhere just to give myself some space. Something that's going to be in the domain of R, but not in the domain of t. What kind of operation can we use? Set difference, exactly, right? Just don't forget. We talk about so many operations in this review lecture, so that's why you want to spend this week putting everything together. And of course, ask me for help if you really need clarification, all right? So we're going to say everything that's in the domain of the original R, but they are not in the domain of t. So these two are equivalent, right? So I think these algebraic properties really have their value. They really kind of force you to think about how individual operations can be composed together. It's so important. When you try to model your system later, very often you may have just model your system as a relation or sometimes partial function, total function, right? That's something we're going to talk about today. You have to, number one, make this decision, justify it. Number two, if you got any operation to really to update that particular mathematical objects, you also need to know how they work. Otherwise, you just get lost. All right. Right, so that's about a very quick walkthrough about the exercises. Please make sure you got them. Okay. All right. And this is where we ended with about the functional property, right? I'm going to, let me repeat very quickly about what we said last time. The way we define the functional property is to say, given a relation may or may not be a function. However, a function is always a relation. All right? Let's draw some very quick diagram here. That's something you want. We're going to draw many diagrams like this today. Think about if this is all possible relation conceptually, a relation. Okay? Oh, you know what? I can do, that's okay. Only a proper subset there is going to be considered as a function that satisfies the functional property. And apparently, you should really consider what can be a member that's actually a relation but not a function. And we gave you one example over here. This one here is a set of pairs. Definitely, it is a relation. However, it is not a function because you can see here for the same domain value over here, they map to more than one range values. That's how you can judge. If that's the case, then it's not a function. All right? And of course, you can go back to the recording from last class just to see how to interpret this predicate here. We try to show to you, if you actually got this particular example here, how can it make this particular predicate false? Right? It's so important. Okay, I want to talk about one more thing that's really important. And then I'll go over some questions and exercises with you. And if you recall, when we talk about predicate logic, how you can prove or disprove some universal quantification, right? That's also relevant here, right? Let me connect. Let's say given this universal quantification, it suggests how you can prove a relation is a function. It also suggests how you may also disprove a given relation is not a function. Let's review that very quickly, okay? If I want to prove that R is a function versus disprove that R is a function. The reason that it is so important for you to see this connection here is because we're going to see many definitions like this. When we talk about injective function, surjective function, bijective function, they all have this universal quantification. So I'm going to talk about just the very first one in detail. Your exercise would be to take a look at the universal quantification for other function types and see how you can prove or disprove it. Right? It will be done in a very similar way. Right? So the others will be left to you. All right, so guys, based on this, how do we prove R is a function? Let me ask first, how many ways are there to prove that a relation is a function? That's number one. How many? Just tell me how many. There's at least one, I can tell you. Not zero, at least one. Just one or more than one? I heard two. Give me one.
For every element of R,
yeah.
It's true that if they all
Absolutely. Thank you so much. That's actually when the relation itself is not empty. Agree? Okay. Number one, you want to prove that for each pair in R. So here, let's clarify some terminology here. This will be what I call the antecedents. This will be what I call the consequence, right? It's easier for me to refer to it. Let's say this is the antecedents. And this one here, let's say that's a consequence. I'll just say, consequence, all right? For each pair in R, which satisfying the antecedents, you want to show that every one of them satisfies the consequence. This is the harder way. You want to show that for every pair in that particular relation, they satisfy this property. Of course, in this layout over here, you ought to find every pair that will actually satisfy this particular antecedent, right? Just be careful. Okay. All right. Oh, you know what? I think, I just noticed that. Sorry, there could be a slight confusion here. Let me do it again, okay? When I talk about antecedents, I really meant this one here. Let me erase this. I beg your pardon. I'll correct that right away. Okay. Of course, this part here is the, you know what? How about this? I think, let's say this is antecedent here, and then I want to put, because the consequence itself is also another implication. I can tell that's a tricky part. All right, you can see that, right? So we got implication here, range and property. For the property itself, we also got an implication, which also got antecedents and also consequence. Let's be very precise what we're doing here. All right? Okay. So let's still call this one antecedents. Let's say antecedent 1. Okay? Let's call this guy here antecedents number 2. Okay. This one here would be antecedents number 2. All right. And let's call this guy here the final consequence. All right. Let's now review this. For approach number 1, you want to make sure for every possible pair you can find, you want to make sure this particular implication is actually true. Okay? So this one here should be the antecedents number 1. And you want to make sure it's satisfied that antecedent 2 implies the consequence, right? It has to be a little bit more complicated than what we talked about before because here we got 2 implications, so that's why. But we'll see more example as we go through the example today, all right? That'll be approach number 1. What about the easier approach? Yes, go ahead.
So for a function, if more than one t map to the same a, that means it's a relation, right?
Yes, that's correct. But you wouldn't say T maps to S because the T is the range. You wouldn't say a range maps to a domain. What you want to say is, if given the same domain value, it cannot map to 2 distinct range values. If it does, like here, you can see it's the same domain value A and A over here, but they somehow map to 1 and 3. And 1 and 3 here are not the same. So that's violates functional property.
Would we compare the domain distance and the consequences?
Yes, for sure. I'm just saying that if you want to prove that this universal quantification is actually true, to really prove that it is true, you have to consider every possible pair. And then for every possible pair, it should be that this particular implication is actually true. So for every possible pair, in that case, this will be one example pair. And then want to make sure the example pair over here can satisfy this implication. You want to show that. And more precisely, if you look at how do you show this particular implication will hold on these 3 pairs, because that one requires S and S, and also T1 and T2. You want to find that kind of pattern. So the only combination I can find is A and A, like a S and S. And then I got 1 and 3 here is like a T1 and T2, right? Once I find that there's such a pair, if there's no such a pair, it's as if the implication antecedent here is false. In that case, false implies anything. Yeah. Mm-hmm. Yeah, guys, I know it's a little bit abstract here. Let's go over the principle first, and then we'll do more example as we go. Okay. So that's one possible way. Is there another way? The other way is an easier one. That means if I simply got this guy over here, just false. There's no such pair. There's no such combination, right? Number 2, show that R is simply just empty. In that case, you cannot find any pair that simply will violate the property of function. In that case, it's a function. So that will correspond to the answer of the first question. What will be the smallest relation satisfying the functional property? Empty relation. Okay? So an empty relation is considered as a function, always. It's simply because you cannot find any witness to prove that otherwise. Alrighty, so now how do we disprove that R is a function? Okay, let's go very quickly. So this one here, there's only one way, right? You want to find that there's some pair over there. However, it will violate this particular property. Okay, let me write it down first. The only way is, first of all, you want to make sure R is not empty. That means you have some combination for you to consider. Okay? And also, there is ST1 in R and ST2 in R, but T1 is not the case of T2. That means you got basically both antecedent being true. However, the consequence over here is simply false. And we saw one example before. You can see we got A and A over here, the same antecedents. But the consequence over here, 1 equals 3, is not the case. So that violates. Right? That's the only way to prove. All right. So that would be the kind of exercise we have to do. Of course, you have to make sure you can also do it. Question?
For T1 equals to 2,
Mm-hmm.
does that mean like, so like for example, the one that you have A, comma 1, B, comma 2, and A, comma 3,
Mm-hmm.
does that mean like T1 and T2 has to be the same?
Has to be the same. Yeah, let me say that again. If you look at this relation here, you want to search for pattern where you got ST1 and ST2. So here we're requiring that the first domain value must be the same as. So this is the only two pairs we can consider, A and A, S and S. And then T1 and T2 over here in general may or may not be the same. But in order to satisfy to be a function, they must be the same. But now in this case, 1 and 3, they are not the same, so they violates the functional property. Yes. Mm-hmm. Very good. Yeah. Yes. No worries.
If they are equal to each other,
Yeah.
then the whole statement would be true, right? Because true implies true is true.
Absolutely. So what does it really mean when they are equal to each other, let's say? So let's say, hypothetically, A and A, S and S. Now let's say 1 here. Let's say I also put 1 over here. A1 and A1. In that way, it would be a function. But the problem is, it's a set. Why would you put A1 and A1 twice, right? So one of them should be gotten rid of anyway. But it will still be, it will be a function. Okay? So I'll just put it aside over here. This will be example number 1. Another example will be if I simply got, let's say, A1 and also B2. So now in this case over here, we cannot find any pair that would fall into, the only pair we can find will be ST1, ST2, will be the A1 itself. Think about A is S, 1 here is T1, and 1 is equal to 1. Yeah, that's the only way. Yeah. Mm-hmm. All right, so we finished discussing also question number 2 about proving and disproving. Number 3. How do we rewrite the functional property using contrapositive? So this one here can maybe help you a little bit more about interpreting the formula. Let's do that. I'll put it aside. Okay, let's now try that. Okay, let's try that. So what I want to do is only this part. Antecedent number 1, I don't want to change it. It belongs to the universal quantification, so I don't want to change it. What I want to change will be this particular part. That's the property, right? For this property here, let's try to rewrite it using contrapositive. So this part here is equivalent to, okay, using contrapositive. And do you guys remember what contrapositive is? If I got P implies Q, it is equivalent to not Q implies not P, right? Yeah, make sure you know that very well. Okay, just put it aside. All right? So what we got is not Q would be not this part. T1 not equal to T2. Okay? If they are not the same, that implies, okay, let's try this. We want to say not the case. Both are in R. If you apply De Morgan, that means either of them is not in R. Agree? Not the case. ST1 in R and ST2 in R. Just for this part, if we apply De Morgan, ST1 not in R, or ST2 not in R. All right, let's make sure the logic makes sense to you first. Let's interpret that intuitively. It says maybe something that's makes more sense to you as opposed to the original one. You can try either way, they're logically equivalent. This one is saying the following. if I have two range values that are different, then either this, well, how about this? Let me write it down more precisely. If T1 and T2 are distinct range values, then we cannot have S mapping to both of them. S mapping to now this part here is really what the logic is saying, that we cannot have S mapping to both of them. That means either S maps to T1 is not in the relation, we don't have that pair, or S maps to T2 is not in that relation. So it cannot be in the relation at the same time, basically. If they are in the relation at the same time, it's going to violate the functional property. Okay? All right. Try to also convince yourself that this part over here is really saying this. Okay? You will definitely need this functional property all the time. So that's why we're spending more time on that. Guys, any question for this? We're good? Okay. I believe there's one little small detail we can talk about, and then we'll take a short break and take attendance. All right. All right, we're done with the exercises. We talk about functional property in lots of detail. And I think that there are some extra exercises. You can take a look on the slides, and you can see in the case where we don't think it's a function, we are disproving, right? And we're going to give some witness. If it is, also you got to justify as well, right? I'll leave that to you. If you got any trouble, let me know. Just more example for you to consider. All right, I think we got total. Okay, how about we'll take a short break now, and then we'll get on to total and partial. Okay, and let me take attendance first. You can get your mobile phone ready, and then we'll do it. All right. All right, you should be able to check in. Okay, good. Yeah, please do it now, and then let's wait for maybe a few seconds. If you got any trouble, please come forward, yes. And I have some sign-up sheet for you. Oh, let me handle this first, and then I'll come to you, yeah. That's okay. All right. Any other issue with you guys? You okay? Okay, I'm going to stop it. All right, done. Let's take a 2-minute break. Don't go too far. Yes. Yes, can you find your name?
Yeah. Right.
Okay, if you, do you have a pen? Yeah, I might have a pen. Yeah. I don't have my pen with me. Yeah, maybe bring your pen. Yeah, please. Hello. You got to be quick. All right, you got to be quick. Got some trouble?
Yeah.
Okay. Did you turn the data plan on? I think you may want to do that for the location service. You may want to. That might help. Okay, just find your last name. Yeah, if you can sign here again. Yeah, as well, please. Do you mind if they use your pen? Yeah.
Maybe this.
All right, quite a good number of them. Thank you.
Thank you.
Okay, I think it's done. Thank you. Trouble?
Listen, it's going to take me forever to check in.
Yeah, maybe just sign up. Yeah, just in case. Yeah, you can just wait after him.
Sorry, Sonate. I can't vote for the last live.
Ah, okay.
I promise I will not be late.
Very good. Very good. All right. And then you got a question? How about I help you maybe after class so I can give you proper attention? How about that? After class. Very good. Yeah, sorted by your last name. Okay, last name. Yeah, just put a check mark here as well, please. Very good. Sorted by your last name. Just look for your last name. Oh. Okay, very good. Yeah, put a check mark and then sign. Okay, we'll start in 1 minute, please. Thank you. Okay, we'll start in just 1 moment. Okay. Alrighty, let's now resume. All right, so the next topic, we have to distinguish between total versus partial function. The reason that we have to make such understand the difference between them is when you make a modeling decision, sometimes you have to distinguish between should I make my mathematical object a partial function or a total function, or should it be a relation? So these are the modeling choices you have to make, right? Let's take a look. Let's see the definition. So let's say given some relation, you can see R is a member of, remember we talk about S relation T. So S relation T here is a set of all possible relations, right? And R is just one of them, right? That's something we talked about before. And what about a partial function? Okay, let's take a look at the definition here. Oh, we'll look at both together, okay? If you look at, first of all, let's understand the syntax. This will be a partial function. This will be a total function. This is how you draw a function in general, like an arrow. In the case it is partial, you will put something like this, partial. Partial in the sense that part of the domain value may not have its corresponding range value. That's what it says. Okay? Let's see. Both of them, let me just put here first. This is a partial function. And this guy here is a total function, syntactically. And both of them are functions, number one. Right? You can see this part here, they share. And in the case of the partial function, the domain of the function there, which is itself also a relation, should be a subset of we're talking about S, right? S is kind of the value you can draw for the domain. That should be a subset. Can be equal, or it can be just a proper subset. On the other hand, if you look at the total function over here, we have something that's very strict. Your domain must be exactly equal to this value over here. It's a very important principle. Okay? Now, based on this definition over here, okay, how do we visualize partial function versus total function? Which one should be bigger? Total? Are you guys sure? Partial? Partial, total? Think about which one is less restrictive. The less restrictive it would be, you can include more members in the set, right? Which one is less restrictive? Partial is less restrictive because in the total there, it's very restrictive because you say your domain must be exactly equal to every possible value for the domain. You include everything, okay? And we're going to definitely talk about some modeling example today, and that will also make more sense. Right? So how do we visualize? What's going to happen is, let's do it this way. Let me try to expand the picture I drew before the break. All right? let's say what we have is this. If we have this very big set over here, that's simply the set of all possible relations. Only those that will satisfy the functional property should be called a function, right? And every function there is a partial function. S partial t. This might sound a little bit intuitive because partial sounds like a special case. Not really. Okay, every function is a partial function. Every function is a partial function. Okay, that's really important to remember. All right, what about total function? Out of those partial functions there will be some where their domain happen to be exactly equal to the left set S over here. They will be called total function. Proper subset over here. S total function T. All right, what can be tricky in your written test and exam, right? Of course, I might just give you some relation. Maybe, let's say, I might just give you R1, R2, R3, right? R1, R2, R3. They're just relation. R1 could be a member in here. R2 could be a member over here. R3 could be a member here. And you ought to know exactly what the difference is. All right, let's talk a little bit more. R1 over here is a relation which violates the functional property. Right? It's purely a relation. All right? I'm talking about just this part over here. Let me be precise. I'm only talking about just this part over here. Right? So R1 is one of them. It's a relation, but it's no way a function because it violates functional property. What about R2? It is a function, but it's not total. Okay? So R2 over here, let's say R2 is a function, but the domain of R is not exactly equal to S. That is, we're excluding the equal over here. That should be a proper subset. All right. Finally, we got R3. That one there is a relation, it's a partial function, it's also a total function at the same time. All right? R3 over here will be something that it's a relation for sure. It's also a partial function. And also is a total function. You want to get these ideas very clear. All right? And we're going to see an example. Okay, let's take a look. The first one over here, let's say I have this notation here. Let's take a look at this one first. Okay, this one here, what I'm highlighting here. So this is the set of all partial functions between these two sets, 1, 2, 3, and also AB. Okay, it's a partial function. A partial function means a function, if it satisfies this, it should be a member of this. It should be that the domain of the function or relation should be a subset of 1, 2, 3. That's the requirements. Okay. So here is, notice what I'm writing here. Just to give you more example, I'm using a subset relation here. So I can give you one example here and one example here. So these are both functions, right? Just notice what I'm doing here. Right? So this will be one function here. This will be another function over here. Okay? First of all, let's take a look at this one here. Is this a partial function? As long as it's a function, it's a partial function, no question. All right? As long as you cannot find any witness to show that it violates the functional property, then it's a partial function for sure. And here you can see 2 is only mapped to just one value A. 1 is mapped to only just one value B, so no violation. Similarly, 2A, 3A, 1B, that's also fine. By the way, you might be wondering, oh, this one looks funny. Somehow these two domain values map to the same range value. Does it violate one functional property? Not really. But it does violate another property called injective property. Well, I'm just want to give you a look ahead. Right? So these 3 pairs over here together also does not violate the functional property. So function 1, function 2. All right? Are we okay with this first example? Yeah, go ahead. No, because partial function is a function. A function is a relation that satisfies the functional property, right? So for example, if you go back to the example here, let's say, take a look at here. This one here, it is a relation, it's a set of pairs. But is it a partial function? No, because these 2 pairs can be used as a witness to show it violates the functional property, as we said before. So this cannot be a partial function. Kind of following? Maybe? Mm-hmm. That's okay. Yeah, we got many examples. Don't worry, we're going to cover it, but you just got to think it through. It takes time. That's why I don't want to release lab 2 that early. Yeah. Mm-hmm. All right, that's okay. But guys, I think that this diagram might just help at some point. All right. All right, how about this one here? Yeah? Yeah, we'll get there. Don't worry. Let's take a look. The second one here, let's take a look. What I'm putting here is, you can see I try to say it's a set of all possible total function, right? As opposed to partial function. Now, total function has more restriction. The domain of your relation or function there must be equal to exactly the left set, which is 1, 2, 3. It must be. Okay? So now, is this a total function? All you got to look at, number 1, it should be a function, right? You can see 2 only maps to one value. 3 only maps to one value. 1 only maps to one value. So it's a function. Is it partial? Yes. It is partial. As soon as it says it's a function, it's a partial function. No question, no brainer. All right. Number 3, is it also a total function? Yes, because 2, 3, 1 here exactly equal to 1, 2, 3. Okay. Let's say this. So this guy over here, let's be also again, number 1, it is a relation because it's just a set of pairs. Number 2, it is a partial function because it does not violate the functional property. Number 3 is also a total function because its domain 2, 3, and 1 is exactly equal to the left set 1, 2, 3. Domain is exactly equal to the left set S. Right? I'm being a little bit informal here when I write it equal, but you know what I meant. All right, hopefully it's getting better, right? Just getting used to the notation. You have some time to actually do this training for yourself. All right, what about the next one? So here we have still a total function here, but I'm showing you one counter example. Can anybody tell me why this is not a total function? Say it again. It's not an element of, yeah, exactly. That's what I put here. So I'm saying that this function here this relation here is not a total function. But why? It's a proper subset. Proper subset. That's the way to put it, yes. It's a proper subset, though that means it's not equal to. Because when you say subset, there's a possibility it might be equal to. Yeah, very good, very good. All right, guys, for this one here, let's make some remark. I think you guys really want to clarify the basic stuff so you wouldn't struggle in the lab later. Okay? Number one, it is a relation, for sure, for the same reason. Number two, it is a partial function because it satisfies the functional property. 2 only maps to A. 1 only maps to B. Number 3, not a total. Not a total function because its domain is 2 and 1. Its domain, which is 2 and 1. Is not equal to the left set, 1, 2, 3. All right? All right, the final one. What about this guy over here? Here, I'm also giving you another example over here that's actually not a total function. All right? So we are still looking at total function here. This guy here, why is that not a total function? Aha, Adnan, that's good. It's not even a function in the first place. How did you figure? Aha, exactly. All right? So here, you got to see, every time you want to see if a relation there is really a total function. Number one, you got to check if it's even a function. Number two, if it will satisfy the total property over here. 2 things you got to check, okay? Apparently, you can see here, 1 and 1. But it maps to 2 values over here, right? So for this example here, number 1, it is a relation. Number 2, not even a function because it violates the functional property over here. So of course, when you say it's not a function, it's not a partial function, it's not a total function for sure. It's not even a function. All right? Maybe your head is spinning, I guess, but it's a good sign. You're thinking. All right? Question?
For the first one, why do we have like two
Oh, yeah. Yeah, you can think about, yeah, sure, no problem. The reason that I'm using this is I can give you 2 examples at one go. Right? I'm trying to say this is a set of all possible partial functions. I'm saying this is one of them. This is also one of them. If you put them together, they should be a subset of that. It's just like a way to show to you, how things work. Yeah. I could have said this alone is a member of this. And also this alone is also a member of this. I could have said that, but it's equivalent. I can put it in one single line.
So that means it's satisfying both.
Yes, so both of them will satisfy the criteria for partial function. Yeah, good. All right, guys, hopefully it's not too heavy, right? You haven't gone to the worst yet. We still got injective, surjective, bijective. Not yet, but we'll see. Okay, let's now move on. And you guys definitely need some study and think it through, and then we'll talk. And how do you write a partial function, total function in Rodin? So you can see the plus over here kind of simulates, right? Over here, you can think about for partial function here. The way you write in ASCII sign would be, you would say the plus and then arrow, like that. You can think about the plus, this vertical bar here is like this, right? Just in case you forgot. And of course, you can look at the resources for your lab 1. Right, quick clarification about relational image and also functional application, right? Now that we know, a relation may be a function, right? So that means when we actually got a function, I can just go to that page directly and then we'll talk about it. First of all, let's review what we had before. Let's say we got the set of all relation here. And we know that only certain parts will satisfy the functional property. And this part over here will just be a partial function. Of course, you also got total function, but let's not worry about total function in this picture here. And if I have a member over here, number 1, it is a relation. Number two, it is a function. It has basically wears two hats. When we talk about a relation, and we have the operation called relational image, remember, right? So let's say this guy here, let's call it f. F, the relation, is also a function, okay? So you can definitely say f being a relation image of some little set over here. Let's talk about it first, and then we'll see why. We can also have some very useful notion about function application. Well, let's talk about relational image. Are you guys convinced that f being a relation here is actually a partial function? That's a partial function, right? You don't have any violation for the property, functional property. Right? That's something we did already. Think it through. Oh, by the way, is this a total function? No, because 3 and 1 is not equal to 1, 2, 3. Right? Good. Okay, so now let's say this is a function and relation at the same time. If I try to do relational image, and if the input set over here happens to be just a singleton set, meaning that it has only one member, what would be the property of the output over here? Even before I write it down, do you guys know any property? What can we say special about if the input here is a singleton set? If the input over here, singleton sets that contains only one element, what can we say about the output? 1 or less? Okay, so now this is 1. If you guess 1, that's a very good guess, but you're missing one case. Because remember, a function in general may be partial, meaning that its domain may not necessarily cover the entire left set. In that case, if you try to do an image on that, it's going to return to you an empty set. Okay, let's take a look. I'll give you one example. Let's say for this particular example here, okay, let me just give you guys some reminder. A relation, a partial function, but not a total function. Okay, just to remind you. All right, let's now try. What would be the relational image for 3? A, or to be more precise, it's a set containing only A. Be very careful. If you only say it's A without the curly bracket, it's wrong. Okay? What about the relational image over just 1? B, right? Agree? Okay. And if a relation already satisfies the functional property, we know that every domain value maps to at most one value. When we say at most, it could be 1 or it could be 0. What about if I say relational image of 2? Empty set, exactly. So that's the special case. Okay? Right? So it's a very quick reminder also about how you can apply relational image when the relation itself is actually a function. Now, for partial function, that means you may have certain relational image that's going to give you some empty. That means it's not defined for that particular domain value. Okay? For a function that is partial but not total, i.e., the domain of f is a proper subset of S. And of course, in this case, this will be S. There is at least one value in S that maps to nothing in F. Right? For example, you can see this is one value 2 that's in S, but somehow it does not map to any value according to this relation or this function here. Right? That's what I'm saying here. All right? And that's about relational image, right? Quick review. How is this related to function application, right? For our convenience, if you pretty much know the relation you're talking about is also a function, you may apply functional application. How do you do that? Easy. This will be the syntax. You will simply say f of 3, f of 1, also f of 2. All right? What will be f of 3? It's not a set anymore. Just say A. And what about B? Only one singleton set B. F of 1. What about f of 2? In this case, undefined. Right? Undefined. You can either say undefined here, and sometimes mathematicians like to use the button symbol over here. That's also undefined. Okay? It's called the button symbol. Okay? Undefined. So whenever you try to do some relational image, it will always give you a set that's either singleton or empty set. But if you try to do functional application, it will always give you one element or undefined. It depends. All right, hopefully it's not too heavy just yet. All right. Okay, so let's see. Everything has been covered, so you guys can take a look. Okay, this one is really good. This one shows to you why we're bothering with so many mathematical, review. This will be give you some feel about how you can use this kind of math. Okay. Let's now consider this example here. Let's now let you read the problem description first. Give me a moment. Let's read it together. Let's say we have some organization that has a system for keeping track of its employee as to where they are in the premises. Let's say, I might say, Jackie should be in, let's say, Life Science Building 106 right now. I might say maybe Adrian, maybe at the other point, it might be in some other lecture hall on the campus. But sometimes it might be that Adrian may be at home. In that case, we cannot keep track of him at the moment. He's not on campus, right? That kind of idea. So what we want to do is we want to have certain mathematical objects to model this concept over here, okay? Given a person that's a member of the institution or campus, we want to know where they are currently, all right? And we want to consider different modeling choices. And in this case, there is right or wrong. Sometimes it may not be right or wrong, but in this case, there will be. Let's take a look. This will be a very nice way to kind of recap about what we have learned so far. And you guys learned about carrier set, right? Back in lab number 1. Let's say we say all the possible employee, we simply use this employee carrier set. Also, all the possible location in that particular company or campus location, lecture hall, office, somewhere. Okay, so we got employee and we got location. There are 3 modeling choices for formulating this tracking software or tracking tool. Okay, either we can say this tracking tool, let's call it where is a relation, or we say where is a total function, or we say where is a partial function. All right. I can tell you that in this scenario, there's only one correct answer, but it's equally important to know why the other 2 are not appropriate. You need to find exactly some scenario that wouldn't make real sense. That's what we're going to do. You got some answer? Yeah, sure. Should be a partial function. Let's start slowly, okay? Yeah, no problem. So, why don't we start, I'm pretty sure you know why the other 2 are not really the case, right? Why don't we start with just relation? Why is relation not an appropriate choice for this?
So, with a relation, we can assume that we could have someone that's not an employee.
Not quite. So we're talking about anyone for us to inquire. It should be a member of employee. Not really. You're getting somewhere, but I tell you, your answer was right. But the justification, not getting there just yet. But thank you for trying. Yes. Let's now see why this is not the case. That cannot be appropriate.
I would say that all
Not quite. For the keep tracking software, of course, a person can switch their location whenever they want to. Yeah, they can do that.
I'll say it's not a regulation because if it was a regulation, then one employee can be in two locations at the same time.
Aha, very good. That sounds very awesome to me. So Ryan, you got a similar answer, I guess. Very good. Think about, whenever you want to think about whether this will be a good modeling choice, you want to think about, is there any pair or subset that's allowed by this relation here that wouldn't make real sense? I can give you one example where it's a relation, but it doesn't make sense. Okay, let me give that to you. What if I have where is that looks like this? Alan, let's say LSB 106. Oh, that should be a pair, of course. Also, I got the same Alan. He might be in Vernier College, let's say 102. This is a relation. Agree? It's a set of pairs. It's a set of pairs, and these values here are employee, and these values are location. It's a relation, legitimate. But does it really make real sense? No. How can Alan be in two different locations at the same time? Right? Cannot be a relation. So, not appropriate. And this is one example to show to you. This is a valid relation, but it doesn't make real sense. Right? You will see on the slide, I also explain that in words. And you kind of get an idea. What about total function? Why is total function not a very good idea for modeling this? Go ahead.
Yeah, so I got it confused. The second one is not supposed, you can't have all employees in the same location.
We say the same location, not necessarily. I can have, in theory, I can have all the employees in maybe some complex, in the company. So that's okay.
But then you're saying like all employees are in a certain work location. They could be on vacation, they could be sick.
Okay.
So not worried.
Yeah, I agree. Yes. So here, you want to think about this. This one is telling you the domain of where is should be exactly equal to the employee. So this is not realistic because, Ryan, you want to say something?
What if outside the building is designated as a single location, and so if you're not in the building, then
Oh, yeah, sure. Right, let's not be that sophisticated. Let's say we only got, let's say as long as you are somehow in that confined area, let's say the company, then somehow you have a way to refer to it.
how would you sort of guess that question?
I think the question there will be quite, I think this one here, either,
I personally made this up.
yeah, if you got doubts, we can definitely ask, during the test to clarify. But I would say in this case, we're saying that as all different spots in the company, they have a way for you to refer to it as a location. Let's say if you're outside maybe some building, but you're still within the campus, we can still find your location. That's the assumption. Of course, if that is not stated in the question, you can always ask to clarify. Yeah. Okay, good. But now, in this one here, it's really realistic. We're saying that all the employees should be in some valid location in the company all the time, unless they never go home. Right? If they ever go home or go vacation, then they will be outside the domain of where it is in the company. So that's why this is not realistic. All right? Hopefully you see what I mean, right? So it's really important to try to link the mathematical object here and their properties to how you can model real life scenario. Okay? So this one here is not realistic. Not realistic to expect all employees to be present in the company all the time. right? It's important to see why the other two alternatives, these two, are not valid. And this one will be just valid. This one is just saying that, it is one to say some employees might just be in the company, in which case we can locate them. For employees, they are not really in the company. In that case, we cannot keep track of them. All right? All right, so this one here is going to be a relation satisfying the functional property but is not total. This is how you should really understand this particular final choice. Yes? Yeah, the first one. If I say it's a relation in general does not really have to satisfy the functional property, meaning that you may have maybe one domain value that maps to more than one range values. In that case, it's a valid relation, but it doesn't really make sense for Alan to exist in two locations at the same time. That wouldn't make sense. That's why we wouldn't choose it. This here, mathematically speaking, is valid, but we are trying to link this to modeling to see what really makes sense. That's the kind of modeling choice you guys will have to make. Right? That's kind of what I said in the beginning of the course. What you learned back in 1090, you may not have so many scenarios for you to really choose a proper model for your system. But now this course will try to give you some idea how you can do it. Once you create a correct model, you can try to do verification, and the result will definitely be relevant. Okay, modeling decision. Okay, and let's now try to do a little bit more. I got about maybe 5 minutes. Okay, let's do some. Okay, and we can definitely finish it within 20 minutes or so on Wednesday. Okay, the next few topics, let me give you a little bit preview. What we need to talk about will be 3 kinds of function: injective, surjective, and bijective. The definition there, how about this? I will talk about some syntax just to help you clarify. But I would say before Wednesday, for you to get the most out of the lecture, I would suggest take a look at the definition for injective. So I start with the definition first. Take a look at them. They are all defined using universal quantification. Think about the critical issue. How do you prove it and how do you disprove it? Okay? And I'm going to go over every example with you on Wednesday, but you may just want to take a look first, like how you can justify whether yes or no they are, for example, injective function. So that's the first slide. And also we got surjective function, which also has what? This one is a bit easier, right? Very straightforward definition. But given that, how do you look at the example? The final one will be bijective function. All right, over here. And we got some extra exercises and etc. Okay. What I want to do now is to give you guys some very quick help on the syntax. Okay. I think that'll be it, and then we'll continue with the formal stuff and example on Wednesday. Let's do this quickly. If I can finish earlier, I'll let you guys all go earlier. Okay. Okay. Functions. So there are 2 aspects or 2 dimensions for you to think about. Either we talk about partial function versus total function. Partial versus total. And the second dimension is, given that it's a function, you can say it's either injective, surjective, or bijective. Okay, so we've got 2 dimensions over here. We already talked about first dimension today, so please try to review it. That will also benefit you for Wednesday's lecture. How do we write them out? Okay, quickly. If I want to write a, let's say, total injection, Injection has its property mainly concerning about the domain, which I'll talk about. So usually you write a total function like this. And now you're concerning a little bit more about the domain. So you're going to put some tail over here. That's a total injection. Take a guess, what should the partial injection look like? We should still have the tail over here. How do you say it's partial? Put something here. All right? Okay. So this will be an injection, but it's partial, so put like that. Okay, I'm just trying to show you, make some logic about deriving the symbols. Okay? Surjective function has to do with more about range. Okay, so if this is a total function, okay, you're going to write something extra in the range side. This is a total function here. You just put another arrow like this. That's a total surjection. Okay? I'm pretty sure you guys know how to write a partial surjection, right? Double-headed arrow here, and then partial. All right? What about bijective function? By definition, it has to do with both the domain and the range. Almost done. The domain and also the range. Right? For the total over here, has to do with the domain. So this part here is the same as this part here. Also has to do with the range. So this part here is the same as this part here. And how about here? Okay, maybe you already know. Okay, no. Okay, by definition, a bijective cannot be partial. It's got to be total. Okay, not applicable. Which is good news. You got one less to remember. Right? All right, I just want to mention to you about the syntax, how you can write it. Make sure you know how to write it on the paper and also on the rodent tool. And on Wednesday, we're going to carry on, talk about these, and then we'll definitely move on to the case study. Thank you. I'll see you on Wednesday.